Well, hello to Math 1342 Statistics class. This is Stephen King. Hope everyone's doing well. So let's continue our discussion with probability. And this lecture video will cover section 13.2. So if you need the help, I hope this can be helpful to you. Okay. All right, let's do some statistics class. Let's begin. We'll go to your MyStatLab and your assignment. Okay, here we go. Okay, statistics class. So I would like for us to begin with problem number 1. And here we go. So we're still looking at probability, and there's just some slightly different possibilities, perhaps we might say. Let's see what we have here. Well, first let me click on the table and make it a little bit larger. Okay, so let's see what we have here. The accompanying table shows the numbers of male and female students in a particular country who received bachelor's degree in business in a recent year. Okay, well, let's look at the table and familiarize ourselves with it. So we have, these are this column is the business degree numbers, and this is the non-business degree numbers at this in this particular country, and they're probably made up numbers, but that's okay. So, and then if you look on the row, there's 2 rows: male students in this country in a recent year, female students in the same country in the same recent year. And so you can see here, for example, there were 182,585 male students who graduated with a business degree in that particular country in that recent year, and 622,427 non-business degrees. And if you add up all the males who have a business degree plus all the males who had a non-business degree, they add up to this 805,012. Female row, we have 178,912 business degrees, 907,651 non-business degrees. So these two total add up to this 1,086,563 female students, again from that particular country in a recent year. If we now add up this column, these 2 numbers, that's the male students who had business degrees plus the females who had business degrees. You add up all those and you get the total number of business degrees in that country in that recent year, totaling 361,497 students. Add up the non-business degrees from both the male and female, they add up to 1,530,078 students. And if you add up, if we now add up the total amount of business degrees plus non-business degrees, you should get the same number as if you add up all the male students and all the female students that year, because these are all the students who graduated that year and received a bachelor's degree of some type. Okay, so if we add this number plus this number, we should get this 1,891,575, and the same if we add up all the males and female students of that year, they would have to add up to the same amount. Okay, so this table has one piece of information in the rows, one category of breaking down the data, and that is by gender, and then the columns is another way, another category to break down this data set. And the research team would have had they collected this data with a certain interest in mind, a certain curiosity, and so that's how they split their data up so that into those categories, gender and by business degree and non-business degree, and therefore resulting in this table, which has 2 rows and 2 columns. Well, these are just the total columns, the sums, and the same with this row here. Okay. So if they ask us, out of all students altogether that graduated with a bachelor's degree that year, that would be this number here. If they said out of all the males, then it would be this 805,012. If they said out of all the females, it would be 1,086,563. If they said out of all the students who had a business degree, then it would be the 361,497, and so forth. So what we're going to learn now is talk about when we look at the entire population of interest for this research team would be all these students, which is this many, that have been broken down into these 1, 2, 3, 4 cells right there, if you will. Yeah. And so if they ask us a question about the entire population of interest, then it's out of this many people, this many students, I should say. If they decide to ask a probability question about only referring to a subgroup, a subset of this population of interest, maybe it's just out of only those students who had a bachelor's degree that year. Then you would only be talking about out of this many, and instead of this many. If they said out of all the females, well, then it would not be based out of this total population data size, but this smaller one, the 1,086,000. So, okay. So let's take a look at letter A. Find the probability that a randomly selected student is male, comma, given that the student received a business degree. So when we read this, we have to say, are they talking about the probability that a randomly selected student is a male out of the entire population of interest, or is it out of a subgroup? So that's what this part right here helps us determine. It says, find the probability you randomly select a student who's male, but pretend every student had an ID number, and the computer could randomly pick a student, and we could program it so that either the computer randomly picks the student from the entire number of students and that graduated with a bachelor's that year, then it would be out of this many student IDs. But if they said pick a random student only from those who have business degrees, well, then it would only be out of this many. And so we would have to tell the computer not to consider all of these people, but only these people right here that graduated with a bachelor's in business. So if they say the probability that a student is a male, well, this is how many males there are. The question is it going to be this many males out of all the students, or this many males out of a subset, a subgroup? So that's what this given part tells us. If they just would have said, find the probability that a randomly selected student is a male, stop. well, then we would write, well, there's 182,585 males out of, actually, there's there's actually this many males and this many males, which add up to this. And then we would say 805,012 out of this many, because this includes the females. And then you would say there's an 805,012 chance out of this 1,891,000 number. So we have to, this is what we're going to learn here in this section is the probability they're asking us, is it out of the original population of interest or is it out of a subset? So here they tell us, given there's like a condition, a restriction, that the student received a business degree. Well, where are all the students who received a business degree? It's this group of males and this group of females, which add up to this many. So we're asking, hey, computer, download all these 361,497 student IDs, because they're the ones that had the business degrees, not these people. Okay, now let's randomly pick one person, one student ID out of the 361,497 students. What's the probability that that one student ID number that the computer spits out, so to speak, is a male? What's the probability? Well, there's this many student IDs, this many students, and there's this many males, so the probability that it would be a male is this many chances out of the total number of chances here, not over here. So let me show you that on my paper. So number one, the probability that a randomly selected student is a male, given that the student has a business degree. And so here's something new right here, and this is this condition, this restriction. So given that the student, we know we're only looking at the students who have business degrees. So this part right here, given that the student has a business degree, that's a restriction on the entire population of interest. It's not the entire, it's not all of these students that add up to this number right here. It's only out of those who have business degrees, which is now this many. And so that's the condition. So, given that the student has a business degree, that indicates that we're looking at a smaller subset or group of the data set. We're looking at a smaller group than the entire population of interest, which were all those students who had degrees, any kind of degree. So here is this little vertical line segment here is a symbolic notation for that. Whatever's afterwards is the condition. It's the restriction that means we're looking at a smaller group versus the entire population of interest. The entire population of interest in this problem were all students who graduated with a bachelor's that year in that particular country. But now we're not, because we have this condition, it's conditioned upon, or we say it's conditional, or we say with the restriction that we're only looking at a smaller group, and that's of those who have a business degree that year. So this is what is meant when we state conditioned on the student has a business degree. Conditionally meaning, again, I'm repeating myself. Yeah, it's a smaller group than the original population of interest. So, well, this condition is the students, out of the students who have a business degree, which is this 361,497, this many here. Now, what goes in the numerator? Well, the question, what is the probability that out of this many people, that you randomly pick one out of this many people, and it's that student ID belongs to a male? Well, there's a lot of chances for it to be a male. There's this many chances, and there's this many chances for the student ID to belong to a female. They could have asked us either question. They just picked one. So it'll be the 182,585 chances out of the 361,497 chances. Okay. So now we just put this in our calculator and then we divide it. So sorry. And that's what I wanted. So now we can do that. So we have the 182,585 divided by the 361,497. And now we just make sure we type the numbers in correctly. We type the numbers in the computer calculator correctly. And we have, and now we look over here, 0.505, and now they want us to round it to 3 decimal places, so we're going to look after the decimal point, 1, 2, 3 digits. Look at the next one, it's a 0, so that means we keep the 5 of 5 and we don't go up to 6, so 0.505. And there it is. And okay. Alright, so that's okay. Letter B, find the probability that a randomly selected student received a business degree. Now, if that's all they said, stop. If there was just a period right here and this wasn't here, pretend it wasn't here, well then, there wouldn't be a condition. You might think, yeah, there is a condition, they have to receive a business degree. Well, that's the question. What's the probability that... So what I'm just saying is that there is a condition, there is a restriction, given that the student is female. So this is the condition. This is the subgroup, the subset. Given that the student is not, it's not from all 4 of these little cells. So it's not all of this number, this number, this number, this number added up together, which would be this. That's what we would put if they didn't have the rest of if they stopped right here after degree. And then we would put this number in the denominator, and then we'd say, what's the probability that the computer would print out a student ID from all of these right here? That's a lot of student IDs. What's the probability that that one ID that the computer prints out, would be a business degree? Well, if that was the question, then you would put this many business degrees. This is how many chances, or how many ID numbers are for students who have a business degree out of the total number of students. And we would put the 361,497 over this big number right here. If the question stopped right here at degree, business degree, period, if it stopped. But it didn't stop. So given that the student is female, well, that changes everything. it does not change the numerator because, well, I take it back. So, given that the student is female, so where are the females in this data set? It's this group right here that have business degrees and this group of females here that do not have business degrees. How many females do they add up to? This number right here, the 1,086,563. So that is our subgroup. Given that the student is from this population data set of interest, which means from this country, bachelor degrees that in that recent year from that particular country, but given that the student is a female, so now it's not out of all of these, because it's only out of a smaller group, only the females. So this number will go on the bottom. So, and now, so given that the student is a female, and this is our subset, this is our group we're looking at, which really are from this little box here, or this little cell, and this little cell. Those are all the females together. Either they had business degrees or they did not, and together the business degree females and the non-degree business students who are females, they add up to this many. So what's the probability? They could have asked, what's the probability that they don't have a business degree? And then we would have put the number of females. What's the chance if you pick one student ID out of all these student IDs right here, which come from this group and this group? What's the probability the computer prints out one student ID number from this group? And they could have asked us, what's the probability that they're from this group or from this group? And they happen to pick this group. What's the probability that they have a business degree? What's the probability that they have a business degree given that the student is a female? Well, this is how many females have a business degree. So there's this many chances. There's this many student IDs of females who have business degrees out of all the females out of all these. And there's this many IDs that don't have a business degree. So there's a much better chance that the ID will be coming from this one, from this group. But the question is, what's the probability to be from this group? So we put this number divided by this number. Okay? So we have the probability that given the student is a female, here's this conditioned on the subgroup, the subset, the female students, which are this many female students. What's the probability that out of this many, which are all the female students, what's the probability they would have a business degree? Well, there's this many students, female students, that had a business degree. So it's this many chances out of this total number of females. And then we would put that in our calculator. And so $178,912 divided by the 1,086,563, and we get double check the numbers, and yes, and we get 0.1646. So we go 3 digits, 164, and then we either keep it a 4 or we keep this third digit past the decimal point a 4, or raise it up to a 5. And because the next digit's a 6, that means we have to go up to a 5 here. So this is closer to 1.165 than it is to 0.164 because of this next digit. So So here we have the 0.165. And that's correct. Okay, and that's what we have right here. Okay, well, let's go on. So the next one I would like to help you with, number 2, is similar. You have a table. So it's very similar. Male, female, instead of business degrees and non-business degrees, contribute and do not contribute. So these have to be complements of each other. Just like these are. When there's only 2, they have to be complements, and same with this. Okay, but that's for you. Number 3. So let's take a look at number 3. This is a non-computational problem. For the given pair of events, well, let's look at the 2 events. So one is flipping a fair coin, meaning it's not imbalanced, it's not cheated, so that one side is more likely to land upwards than the other side. So it's fair. So one event is we flip the coin and the tails appears upward. That's the visible side of the coin. And now another event is flip the same coin a second time, again. Flip it again, which means a second time, and then you get a heads facing up. So the question is, should we think that, you know what, there's a better, because the first time the coin was flipped, a tails came up, so therefore probably there's a better chance next time that a heads will come up, because last time a tails came up. That's what they're asking. Is that really proper logic? Like, if you ever seen the game roulette, there's a spinning wheel. I think we did a problem in the last section or something about the roulette in 3.1 actually. And the wheel spins, and there's half the numbers, almost half. There's the 0 and there's the double 0 slot, remember? And then however big the wheel is, there might be, pretend, 29 numbers. Let's say it's from 1, or say it's 1 to 60. And then half of them are red and half of them are black slots. And so maybe number 1 is red and number 2 is black and number 3 is red and number 4 is black, like that. And the 0 and the double 0 are both green tiles where the ball can land, the middle ball. So if you ever seen the game like at a casino or something, what they do is they'll spin the wheel, throw the ball in, drop the ball in, the ball drops in. They don't put it in their hands or anything, I don't believe. And then the wheel slows down, the ball slows down as well, and eventually it lands in a slot. You just pretend it lands on black 10. And then on a little computer, some kind of screen or some kind of monitor, they'll show, okay, black 10. And then they'll play the next try. And then just pretend it says black 12. And then the next try, black 30. And the next try, black 44. And you're like, they put that up there, and then the bettor says, boy, there's been 4 blacks in a row. The ball landed on black 4 times in a row. I'm going red. And I'm putting all my money in my piggy bank, all $12 of it, and I'm putting it on red. because it already landed the last 4 times it was on black, so chances are it's going to be red now. Is that sound logic? Not to mention, is it sound gambling logic? So those screens that pop up, yeah, the next spin and where the ball is going to land, assuming there's no cheating going on and the game is true, then what happens on the next game, on the next spin, whatever will happen on the next spin will not be influenced by anything that has happened in the past. Whether it was the previous 4 spins or the 100 spins from a week ago, it has no impact. Every game starts new, and the outcome of the next spin is not influenced or impacted at all by what just happened before. So though they put that up there, but it's for nothing. Well, except to try to confuse or maybe deceive people that are playing the game and gambling, thinking that, oh, I'm going red or whatever. So the same idea here. We flip a fair coin and get a tails, and then we take the same coin and we flip it again, and it becomes heads. Is this second event influenced at all by what happened on the first toss? Well, I hope I've convinced you that the answer is that this second coin toss is not influenced at all by what happened on the first toss. So then this second event is not influenced, is not depending, is not dependent on what happened on this first one. They're completely, the second one is completely not influenced. It's not impacted by what happened on the first toss. The second toss is independent. What will happen on this second toss is completely independent of what happened on the first toss. So we call these two events independent. So now we look for that. That says dependent. Independent. The 2 middle ones are independent. So it's one of these 2. So B, the 2 events are independent because the occurrence of one does not affect the probability of the occurrence of the other. The occurrence of one does not affect the probability or the outcome of what the other will turn out to be. Getting this, the chance of getting a heads on the second toss, it's still 50%, regardless of what happened on the first toss. So this probability of the coin becoming a heads, it's 1/2 or 50% chance, and it's not influenced at all by what happened on the first toss. The occurrence of one event does not affect what will happen, what will occur on the other event. Or you can say it will not affect, another way of saying that is, what happened on the first event what will happen on this second event is not influenced. The probability of it happening is not influenced. It's not impacted by what happened on the first toss. And this one says they're independent because the occurrence of one event affects the probability of the other. Well, that's what we're trying to say is not the case. So it's letter D. Okay, good job. Next, I'd like to help with number 4. Here's another situation talking about dependent and independent. Determine whether the events we're about to state, let's see what they are. So one event is returning a rented movie after the due date. You can tell this question's getting old because people don't really rent movies anymore. Those days have gone. You went to Blockbuster or Hollywood Video. I'm showing my age. You guys are so young. You might. I guess you're not. You would remember it as a kid or something, probably. Okay. So returning a rented movie after the due date, now you got to pay a fine, or at least there's a chance you're going to pay a fine or a fee. So so here's the second event, and receiving. That's a nice way of putting it. Receiving a late fee. I guess you receive it, and then it's up to that person to pay it or not. So one event is returning a rented movie after the due date. And now the second event is receiving a late fee. So, is this second event, is it impacted by this event? So, another way to say is it impacted or influenced. Another way to say it is, does the probability of this second event change, meaning it may be larger, a larger chance or a smaller chance of happening if this first event, if we know what happened on the first event, if this event has occurred. You returned a rented movie after the due date, that would influence this. Yeah. Or you can say this is influenced by this. You can say this would impact this. This would have an impact, an influence on this. Or you can say receiving a late fee is influenced by this event. Yeah. If this happened, we returned a rented movie after the due date, then the chance of this event happening goes up. So this event is influenced, it is dependent on this event. So these events are dependent. The events are dependent because the outcome of returning a rented movie after the due date does not affect the probability of the outcome of receiving a late fee. Does not affect or does affect? It does affect. Yeah, it affects it. It would raise it. They could make a mistake, or they could be nice and not charge you the late fee, but you don't know it until you get there and return it in the late movie, and then you find out. But this certainly would have an impact on this. So they are dependent. Number 5 is similar. I'll leave that one for you. And also number 6. So next I'd like to help you with number 7. Now we have to know a little bit about the standard deck of cards. So some people are very familiar with the standard playing deck of cards and some may not. So I'd like to show you a picture of a standard deck. So here class, here's a picture. Well, it's a picture of the standard deck of playing cards. And this is on page 134 of your textbook or your e-textbook. Or you could just search it on a browser. Standard deck of playing cards. And if you're not aware, this card deck is just the group of all of the cards, is broken down into 4 equal categories or types of cards, or they call them suits. Hearts, you can see the shape hearts. Diamonds is a second suit, and these are the 2 red suits. So half of the cards are red suits and the other half are black colored suits. And these are called spades. I guess it kind of has the shape of a shovel, sort of. Spade. Clubs. I'm not sure. Clover. I don't know where the club came from. I'm sure there's a reason. But there's an equal number of clubs, spades, diamonds, and hearts. And if you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 hearts, 13 diamonds, 13 spades, 13 clubs. 13, 13, 13, and 13 are 52 cards. 52 cards in a standard plain deck. Usually they come with 2 jokers, and if you throw them in, you would have 54. But the standard deck is just considered these 52. Now, of these 52, each suit, each category, they have 13 each, and they have the same type of card. Starting with A stands for ace, A-C-E. K stands for king. Nice name, I like that. That's my favorite card. Q is for queen. J is for jack. King, queen, and jack, these cards have faces on them. The face of a king, the face of a queen, and the face of a jack. All the other cards do not have faces. So these king, jack, king, queen, jack are called the face cards. All the others are called non-face cards. And then after that you have a 10, 9, 8, 7, 6, 5, 4, 3, 2. So 10 on down and the ace are the non-face cards. So then we have, for example, 4 queens, 4 kings, 4 aces, 4 jacks, 4 tens, all the way down to 4 twos. So, okay. So the question is going to be, on the problem we were about to look at is, what's the probability we shuffle all these cards and maybe we spread them all over the place on the table or something, and or say it's from a computer and the deck is in the computer, and then you ask the computer to randomly pick one card, a first card. And, well, every card would have the same equal chance as any other card, as long as it's fair. So any card would have a 1 out of 52 chance, because there's 52 cards here. A 9 is just as good a chance as a 7, or as a 2, or as a king, or anything else. So if they ask you, hey, what's the chance the first card is a 8? Well, you'd say, okay, well, I know there's 8 of hearts, 8 of diamonds, 8 of spades, 8 of clubs. I know there's 4 8s. So there's 4 chances out of 52 cards altogether. There's 4 chances out of 52 total chances that the card will be an 8. I don't think we want to bet all the money left in our piggy bank on that card randomly popping up 8. Not a very good chance. Now, what if we put the card, let's say we pick the card, any card. See, there's a different, it's easy to get a little bit confused on what I'm about to say. When we say what's the probability that the card picked will be an 8, and then we actually do this experiment and we pick a card at random, well, what's going to happen? Either the card is going to be an 8 or it's not going to be an 8. Most likely it will not be an 8. And we'll say, darn it, and there we lose our money in our piggy bank. Unless the card that is picked is an 8, happens to be an 8, well, then we win, so to speak. So when we say what's the probability that the card will be an 8, and then we say there's 4 chances out of 52, well, that's the total. You have 4 chances out of 52, but you only pick one card. But because 4 of them in that deck have a number 8 on it, out of 52 total cards, then you have a 4 out of 52 chance. Now, if they said, throw the card back in the deck now, and mix all the cards up again, well, now, since we put that first card back in, now there's 52 cards again. And then they might say, okay, what's the probability that, now pick a second card. Pick a second card. And what's the probability that that card will be a 5? Have a 5 on it. You'd say, okay, well, since I put the first card back in, there's 52 cards. And the chances of it being the card that I pick, the chances that it's a 5 is not a very good chance, because there's only 4 of them. These 4 out of the whole deck. And then you would say 4 out of 52 again. Now, if they ask you, what's the probability that the first card you pick is an 8, you would say, okay, 4 out of 52. And then they say, and now throw the card back in and pick a second card. Oh, now here's a second thing. And what's the probability? And then the question is, what's the probability that that one would be a 5? Well, then that probability would be also, again, 4 out of 52. And then you'd have to multiply those two probabilities together. 4 out of 52 for the first card to be an 8, and times 4 out of 52 again for the second card to be a 5. But what if we did not we pick the first card and we do not put it back in the deck? We keep it in our out of the deck. Well, now we're not saying that you actually get an 8 when you pick the first card. So here's the question. What's the probability that the first card you pick is an 8 and the second card you pick is a 5? But don't put the first card back in the deck this time. Keep it in your hand. So then we'll say, okay, the probability the first card is an 8 is 4 chances out of 52, 4 over 52, times, what was the second thing? Oh, the probability that the second card will be a 5. There's 4 5s, so there's 4 chances. But it's not out of 52 cards anymore because we kept the first card in our hand and did not put it back in the deck. So then there's only 51 cards left, and the chance that it would be a 5 is 4 chances out of 51. Now, but it can be confusing, potentially confusing, because it's easy for us to think, well, I don't know if the first card was an 8 or not, or the second card is a 5 or not, until I look. Well, yes. But the question that's being asked of us, to us, that we're practicing, is not, does the 8 actually show up on the first card you pick, and then on the second card, does a 5 show up? I mean, it's very unlikely that it's going to happen. That's not the question. The question is, what's the probability that it would happen? So when we pick the first card, it's probably not going to be an 8. But that's not the question. The question is, what's the chance that it will be an 8? And the chance that it will be an 8 is 4 out of 52. Most likely it will not be an 8 and we lose the game. But that's not what they're asking. If we lose or win, they're asking, what's the chance that you would get an 8? And on the second card, get a 5. So when they ask us that, that's different than saying, did it actually happen? So to answer it, we have to say, okay, the chance that it will get an 8 on the first card is 4 out of 52. That doesn't mean you actually got the 8, but that's just the chance that you would get it, 4 out of 52. And then for the second card to be a 5, they're not saying it's going to happen. They're just asking, what's the chance? Well, the first card, the question is, what's the chance that you get a 8 and then a 5? Well, the chance that it's an 8 is 4 to 52. The chance that the second card is a 5 is, given that the first card was an 8, which may or may not happen, but we know the probability of it happening is 4 to 52, times the probability the second card is a 5 is 4 out of 51. So that's what we're going to do. Two cards are selected from a standard deck of 52 playing cards. The first card is not replaced, like I mentioned, before the second card is selected. So find the probability of selecting an 8 and then selecting a 5. So I have here number 5, the probability, PROB, open parenthesis, close parenthesis, and whatever they're asking us, we have inside. Select an 8. I'm not going to write the whole paragraph here or sentences. Select an 8 on the first card and select a 5 on the second card, knowing that you do not, after you pick the first card, you don't put it back in the deck. Okay, so by our discussion and sort of by intuition, this question right here is equal to saying the probability of selecting an 8 times the probability that we select a 5, given that we already selected an 8 on the first try. Again, it doesn't mean that it's going to happen. It doesn't mean, oh, I did actually, I got an 8 on the first card and then I got a 5 on the second card. Wow, that's incredible. Well, that would be incredible because it almost never will happen. If they're asking, is this very likely to happen, we would say no. But that's not what they're asking. They're saying, what's the chance that it will happen? And if it happens, then you have to get an 8 on the first try. What's the chance of getting an 8 on the first try? It's 4 chances out of 52. And then we're asking, what's the probability then you get a 5 on the second selected card? They're not asking us if it happened or not. It's just, what's the probability that it happens? Well, the chance is to get a 5, given that we already selected an 8, which means the 4 5s are still in the deck. And so there's 4 chances then out of 51. And now we multiply these two probabilities. Probability of selecting an 8 times the probability of selecting a 5 given condition upon that the first card was selected was an 8. That's what this little condition means. So this probability is 4 to 52 times this probability is 4 to 51. Multiply these together with a calculator. And there we go. 0.006. Look at the next digit. Should we change this to a 7 or keep it a 6? Well, this is 6 zeros, so that's closer to, so we keep this as a 6. If that was a 5 or a 6 or a 7 or 8 or 9, then we would round it up to a 7. Okay, so there we go. So another definition of unusual. So we had unusual so far. The first case, it was when we're more than 2 standard deviations away from the mean, and that would be considered unusual. More than 2 standard deviations away from the mean value of your data set. And then we had a definition of, it wasn't actually unusual, but it was an outlier. An outlier, a data point being an outlier, and then when we compute the 5-number summary, and then we draw a box and whisker plot, a data point is an outlier if you are either the data point is past the 3rd quartile or less than the 1st quartile value, but it has to be 1.5 IQR beyond the 3rd quartile, or 1.5 times the IQR value in front of quartile 1 value, without reteaching that. Here now we have another definition of unusual event, and I may have mentioned this before, but statistically they say if your probability value is less or equal to 0.05, or you could say 0.50 if you like, and 0.05 is 5% chance. So if your probability value is either equal to 5%, equal to 0.05, or smaller than 0.05, less than, then we call that an unusual event, statistically speaking. So what about drawing an 8 on the first selected card, and then keeping the card, and then getting a 5 on the second selected card? The probability of that happening is 0.006. And 0.006 is less than 0.050. This is way less than this. So this would be considered an unusual event. It's so unusual. If you were playing a a friendly game with your friends or family, and it's supposed to be fair, and they said, let's have a crazy bet. Can you get an 8 on the first card and a 5 on the second? And it actually happened. This is so rare, I would be a little suspicious if this was set up or not. So you would be suspicious. It would just be, I mean, it can happen, but it's a very, very small chance. Okay. Anyway. So to use this problem as an introduction to these formulas, I wrote here. So this is the answer, 0.006. And there we go. And we'd be done. But I want to show you this on my notebook for the future problems. So we can also compute this probability question using the actual probability formula. So let's talk about the probability of a first event occurring. What event? Whatever it happens to be, and we'll just say event X. Why X? There's no reason. It could be S, T, or whatever. And the probability of the first event, say it's called event X, and the second event, say it's called Y, occurring, just like this one up here was selecting an 8 and then select a 5 next. We did this sort of by intuition, by discussion, kind of by logic, but I want to go over the actual formula as well. So if you have a question that asks you for the probability of a first event occurring and the probability of a second event occurring, then we can use this probability formula, which is this right here equals the probability of the first event, I just named it X, occurring. The probability that the first event X occurred, which in this case was the 8, and there were 4 out of 52 chances for that, times, there's a dot right there, multiplied times by, well, the probability that the second event has to occur, because both of them have to occur, and this is the first one and this is the second one, so it should make sense that it's equal to the probability that the first one occurs times the probability the second event occurs, but given that the first event occurred, and we know the first event occurred. So, yeah. So the second event was selecting a card that's a 5, knowing that the first card selected was an 8. The probability that the second card is a 5, given that the first card was an 8. And this probability here was the probability you could get a 5, knowing that the first card selected was an 8, and we didn't put the card back in to the deck, was 4 chances out of 51. To write that a little bit shorter, instead of probability first event X occurring and so forth, you could say the probability of X and Y equals the probability of the first event, X, times the probability of the second one, Y, given that X has occurred. Shorter yet, instead of PROB, P for probability, X, this little symbol here is for and Y, X and Y. Sometimes they use the word intersection as well. X intersect Y, X and Y. Both have to happen. equals, instead of PROB, P of X, probability of X, times P of Y given that X occurred. Thus, in this exercise 5 up here, the probability of getting an 8 on the first selection and a 5 on the second selection equals the probability of the first one, selecting an 8, times the probability of the second event, which is getting a 5, knowing though the first card was an 8. And that's the same computation that we did above. The probability of selecting an 8 was 4 out of 52 times the probability of selecting a 5 is 4 out of 51 because we didn't put the first card back in the deck. And we know there's 4 chances to get a 5 out of 51 cards if the first card was a 8. And if you multiply that, we get the 0.006, same answer as above. Okay. So we're going to keep using this now. So let's go on. So next, that was number 7. I'd like to help you with number 8 now. So here we go. So now they're going to describe, they're going to talk about 2 events occurring, and then they're going to ask us something about that. The probability of the first event and the probability of the second event occurring. So what's the first event? Not selecting a card, but toss a coin. Toss a coin. And then the second event is you take an 8-sided die, 8-sided cube with numbers 1, 2, 3, 4, 5, 6, 7, 8 on all the 8 sides. I mean, 1 is on one side and 2 is on another side, of course. What's the probability of tossing a coin and it landing heads up? And the second event is you roll the 8-sided die and you get a number showing face up. That is, it could be a 1, a 2, a 3, a 4, a 5, a 6, a 7, or 8. But the question is, it has to be, the number facing up has to be greater than 6, than a 6. So the probability of the coin toss landing heads up and rolling a die and the number facing up is greater than 6. Okay. So now I'm going to start to write the events that they're talking about. And then in this probability statement, we can not write so many words. And it's cleaner this way. I didn't do it on the first 2 or 3, but now I want to start doing it. So one of the events is a coin toss landing heads up. I'm just making up the name. We'll call this, it's an event. This is what's happening. But I'm going to make up the name of the event. I'll just call it capital H for symbolizing heads up. You could call this event P or event Q or event X or event A, whatever. And the second event is rolling the die, an 8-sided die, and getting the number that lands face up is greater than a 6. I just put event S for greater than the 6. I mean, you can name it anything you want. I just don't want to have to write all this down inside this parenthesis. It gets messy. But we have it right here. Okay. So, then in the question, the probability statement question can be written succinctly here, briefly, concisely, by just writing P for probability, open parenthesis, close parenthesis. What's inside? Whatever the events are they're asking, which are event H and event S occurring. Which is what again? Oh, the coin tosses, lands heads up, and roll the 8-sided die and a number greater than 6 lands heads up. S. What do we know? The probability of an event and a second event occurring. What is it equal to by the probability formula? So remember, we just talked about that. And that was this right here. The probability of an event X and a second event Y equals the probability of the first event times the probability of the second event occurring, given knowing with the restriction that the first event occurred. Knowing the first event occurred. It did occur. So, okay, so the probability of event H and event S occurring equals, by the probability formula, equals the probability of the first event occurring, which is the probability of H occurring, which is the probability the coin toss lands heads up. And if it's a fair coin, it's either going to land heads or tails. So we say there's a 1 chance out of 2 that it'll land heads up. Times the probability of the second event occurring, which is you roll the 8-sided die now, and a number lands up that's greater than a 6. Well, what are the numbers greater than 6 on an 8-sided die? Well, there's only a 7 possibly, or an 8 possibly. So there's a 7 or an 8. That's 2 chances. 2 chances that it could be greater than a 6. 2 chances out of 8 total chance, total possibilities. So there's a 2 out of 8 chance that event S will happen, knowing that event H occurred. So now we multiply 1/2 times 2 over 8. Multiply that on a calculator and we get 0.125. 0.125, which is right here. Correct. .125. So if that makes sense. I want to mention one more thing here. Notice this conditional probability statement right here. The probability that event S happens knowing, given, conditioned upon, conditionally that we know event H occurred, the coin landed heads up. Well, knowing that the coin landed heads up on the first event, does that have any impact on the second event, in this case, of the die landing greater than a 6? Well, the whatever happens when you roll this die is not impacted, it's not influenced by this first event occurring. So these are independent events. So the probability that event S occurs, you roll the die and you get greater than a 6. Yes, we are writing the probability, and we have to. The probability that S occurs given that H occurred. It's just that knowing that H occurred, knowing that the coin landed heads up, does not influence this probability of event S. Note, in this situation, events H and S are independent. When that's the case, thus the probability of event S occurring, knowing given restricted condition upon that event H occurred, because this does not impact this one, or you can, another way to say it is, this is not impacted by this one. The probability of this happening is not impacted by this event occurring. It does not change the probability of this. So then, when they are independent, then we know that this did not impact this. And therefore, the probability of event S, given knowing conditioned on event H occurring, having to occurred, and the probability of just S by itself, the probability of rolling the die and getting greater than a 6, this probability and this probability have the same value. They're equal. Because, again, this does not impact the probability of this one. So when they are independent, we can say we know those are equal, or we can write this. They're the same. Okay. So that's number 8. Next, number 9. So, research has shown that approximately 1 woman in 400, 1 in 400 women carry this mutated gene, a particular gene that they are interested in, but it's mutated, and that may or may not have an impact on the woman's health, or who knows. That's what research is doing. But they're telling us the research. They're saying, firstly, 1 woman out of 400 is the proportion of women who have this particular gene that women have, but it's mutated. Something changed in it. Okay. Now, if the woman has this mutated particular gene, then they know, the researchers know, that about 71% of the women that have this mutated gene they develop, unfortunately, skin cancer. We don't know if this data is true or just made up, but that's what the problem is stating. So, we may think, oh, 1 in 400 is a lot, or we might think, oh, it's not a lot. 1 out of 400 have this mutated gene. Regardless of that, but if a woman has this, knows that they have this mutated gene, then the chances of them having skin cancer is 71%. So, and since I think it's fair to say 71% of women in general, just generally speaking, all women put together, I don't think 71% of them develop skin cancer. It would be much, 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 much lower than that. The lower the better, huh? So, the fact that they know if the woman has this mutated particular gene, then it really raises the probability that they would have developed skin cancer eventually. So, the event, a woman carrying this mutated gene and the event developing skin cancer, they are dependent. Developing the skin cancer is heavily influenced by the knowledge, or it's impacted heavily by having this mutated gene. So these are dependent events. Okay. Question. Find the probability that a randomly selected woman will carry the mutation of this particular gene. Now we got to be careful. Are they going to say given or and? Probability of randomly selecting a woman who has this mutated gene and will develop skin cancer. So there's the and. So we're going to use the probability of one event and another event occurring. So number 9, let's call a woman carries this specific mutated gene. It's an event, not a positive event, but it's an event. And I just picked a letter to name it. And I just said capital M for mutated. Event M. The woman develops skin cancer. Event, not a good thing, not a good event, not a positive event. Event C, I just picked C for cancer. Not any kind of cancer, it's skin cancer. Question, find the probability that event M and event C occurs. They're not saying that you randomly pick a woman and it's going to happen. They're saying, what's the probability you randomly pick a woman from the population and that woman has the mutated gene and has developed skin cancer? Well then, according to our definition of the probability of an event and a second event, that's equal to the probability of the first event, which is 1 out of 400, times the probability of the second event developing skin cancer, given that they already have, that we know they have this first event occurred, mutated. The woman has the mutated gene. So we know the probability that a woman will carry this specific gene is 1 out of 400. So we write it down. Times the probability that a woman will develop skin cancer, given conditionally knowing that they have this particular gene, is 71%, 0.71. And thank goodness it's not a 71% chance of developing skin cancer. It's a 71% of those who have this. So it's not 71% of the general women population, it's 71% of this. And now we multiply those together, and we get about 0.0018. We check. So we have the probability of the first event, 1 out of 400 times, oops, the probability of a woman developing skin cancer knowing that they have this gene, the 71%, 0.71, it's 0.0017 and so forth. And they say round the answer to 4 decimal places, 4 digits past the decimal place, point position. So 1, 2, 3, 4, so that's a 7. Now either we leave it a 7 or we go up to an 8. It depends what follows. What follows? A 7. So the 7 means this is instead of 1.7, it's closer to 1.8. So we put a 0.0018. And that's the correct answer. I also want to mention here, to remind ourselves, would this be considered then this event, this situation, randomly selecting a woman out of the entire population of women, and the women would have this mutated gene and have developed skin cancer? Is that a very high, is that very likely? Or is it unusual? Well, the chance that it would happen, according to our computations and according to the data that they gave us, the data results from the research, it's 0.0018. And that's 0.0018, thank goodness, is way less, a lot less than 0.05. This number here is a lot smaller than this, thank goodness. So that would be considered an unusual event. Okay. So number 9. Okay, next that's number 9, as you can see. Number 10 and 11 are very close, so I want to do number 11 with you instead of number 10. So let's look at number 11. So number 11, it tells us here, class, in a survey of United States adults with a sample of 2,069 adults were surveyed. And they were asked if Franklin Delano Roosevelt was the best president since World War II. And either in their survey they would say yes or they would say no. Who knows what other questions were being asked, but this is what we're looking at. 367 out of 2,069 adults stated that Franklin Roosevelt was the best president since World War II. Okay. We're not to question this, if it's realistic or not realistic, true, untrue. This is the results of the survey. Now, knowing that, now later on in the course we can talk about should we question this based on some other information, but that's not the intention of this question. For now, they're now going to ask us, if we randomly select a first adult from this survey, so let's say the 2,069 people, adults, filled out the survey, and then there was a identification number at the top of the form. The person doesn't put their name on. well, let's say they do put their name, or let's say they put their name on it, but now the data goes into the computer, and now the computer takes the name off and only leaves the identification number. Now, we have 2,069 survey results that all have an individual identification number, which represents one of each adult in the 2,069. Now have the computer randomly select one of those 2,069 identification numbers, and what's the probability that that one identification number, the first one the computer picks, will be from that identification number will be from a person, from an adult who stated that FDR was their favorite president, or no, was the best president since World War II. And then, without putting that person back into the computer, so to speak, now there's one less person, so there's only now 2,068 identification numbers in the computer because one has been taken out. What's the probability that the second adult, the second identification number the computer prints out, will be an adult who stated that they believe FDR was the best president since World War II? Also, they're not asking us if this would happen. Most likely it would not happen. Pick one identification number, check it. Most likely it won't be a person who stated FDR was the best president, because not that many people did. Only 367 out of 2,069. And then a second person also randomly picked who said, again, FDR was the best president since World War II. So this happening twice in a row is going to be unlikely. We'll find out if it's unusual as well. Okay. Without replacement, just like with the card, you don't get to put the card back in the deck after you pick the first card out. The same idea here. They're not asking whether or not this will happen. They're asking us, what's the probability that it will happen, that it would happen? So then we have to say, okay, there's, for the first person picked, randomly picked, there's 367 chances out of 2,069. Times the second person, they're not asking if they're not asking us, they're saying what is the probability that the second person would also state that they felt that FDR was the best president. And so now you would say, well, now there's, because the first person was picked, said FDR was the president. Remember, they're not asking if this happened. We won't know. They're saying if it does happen, what's the probability that it will happen? So we have to say it will happen. Now, what's the chance that it will happen? Well, it's 367 out of 269, 2,069. $367 out of 2,069 times, well, now there's one less person left So there's only 2,068 people left. And there's only 366 people left that stated that FDR was the best president. So then the probability that the second person selected would also state that is the 366 chances out of 2,068. And we'll multiply those together, and we'll get approximately 0.031. This would be called an unusual event since 0.031 is less than 0.050. 0.50. 0.31 is smaller, less than 0.50. This is a 3.1% chance, and that's smaller than 5% chance. Notationally, kind of jumped ahead a little bit. Adult states from the survey, you randomly select an adult that filled out the survey, randomly select an adult, and that adult was one who stated that FDR was the best president since World War II. And so that's an event. And so we name it something. I just called it B for best president, but you could name it anything else. So find the probability that, in grouping open parenthesis, close parenthesis, B1 I just wrote, it's just my way, it's not a perfect way, it's not the way the author may have written it, it's not the way you have to write it, it's just the way I wrote it. It's a way for me to say, okay, the first adult picked first, second, and event B happened. It occurred. What's the problem? They're not asking us, again, they're asking us what's the probability that this would happen? Not whether it happened or not. It's just that what's the probability that it would happen? B1. First adult picked is one who stated FDR was the best president, and the second adult picked also stated FDR was the best president. What's the probability of that happen? The first person and the second person are both stating that FDR was the best president since World War II. Well, using the definition again, it's equal to the probability of the first event occurring times the probability of the second event occurring, given, knowing, conditioned upon that the first event occurred. The first person selected, stated FDR was the best president. And then we get these numbers. Okay. So 0.031. So that's what we have. Good. B. Find the probability when you pick 2 U.S. adults again from this sample group of 2,069. Now, what's the probability that, not that both people stated Franklin Roosevelt was the best president, but the probability that neither adult, the two, you picked one and they did not state, they did not say or believe that FDR was the best president. And also the second person picked did not believe FDR was the best president. So that's what letter B is asking. Okay. Here is this so since I called this event B is where an adult was randomly picked and they were an adult who stated FDR was the best president since World War II. Then if you put a prime right here, prime, that means the complement. Remember we talked about that as well in the last section, 3.1. So B prime, B complement, would be the complement of this, which is the other part, the ones that are not this, the adults that are not in this group. So what adults would not be in this group? They would be the adults that were in this survey group that stated FDR was not the best president. So, in my notation, the probability then, the first adult picked from the 2069, prime means they did not state FDR was the best president. And the B prime complement, the second adult picked did not state FDR was the best president. Well, using our probability formula, that is equal to the probability of the first event, which is this, the first person did not state FDR was the best president, times the probability that the second person selected did not state FDR was the best president, giving that the first event occurred, which is the first person did not state FDR was the best president. I'm getting tired of saying that. You might be getting tired of hearing that. Don't tell me. Well, how many people, this many people stated that they believed that FDR was the best president out of 2069. So if you subtract 2069 minus 367, we get 1,702. And that's how many adults would be in the complementary group, would be in the B prime group. Because they would have stated that FDR was not the best president since World War II. So, to compute this, we have to know this. 1702. So 1,702 adults stated that FDR was not the best president since World War II. So then what's the probability of this? The first adult picked not stating FDR was the best president. Well, there's 1,702 adults that said that FDR was not the best president out of the 2,069 altogether who filled out the survey, times, now there's one person out already from the group, so there's only 2,068 left. And since they're asking us what's the probability that both people would state FDR was not the best president, then we have to say, they're asking what's the probability of this happening. So that means we have to say, oh, this means on the first pick, it was a person who stated FDR was not the best president. So now there's only 1,701 adults left that would say FDR was not the best president out of now not 2,069 people, but 2,068. And now we multiply these together and we get 0.677. 0.677. .676. The next digit's a 6, so then we round this up to a 7. So 0.677. So that's done. But I want to show you one thing, and that is if we would have if we would have put the first person back in the group after they were selected, well then, and now pick again, well now there would still be in the denominator 2069. And in the numerator, if you put the person back in, then there would be 1,702 again. That stated FDR was not the best president. We would multiply those together. And if we would have done that with the directions to leave the person out, like we were supposed to up here, we left the first person out. But because there were so many people, notice this little error of putting the first person back in, it doesn't change the answer very much. 0.6767. It changes it when you get to the fourth digit. So on this problem, if they said round to 3 digits and we would have made this mistake, it wouldn't have impacted our answer. If they would have said to 4 digits, then it would have impacted it. But if this was in the millions, which is, I'm stating this because there's a problem coming up where it'll be in the hundreds of millions, and then it really won't matter if they say you're supposed to leave the person out and you put them back in. Because the numbers are so big, it doesn't really affect the probability. So I'm going to be making that comment again in a couple soon. Okay, but back to this one. Letter C. Before I read letter C, I want to just make up a little just make up some example just to try to put our brains in the right place. So, I don't know why this came to my mind, but when I was thinking about what to say, but just pretend when we were kids, and for some of you that's not very long ago, but just pretend. So pretend there's a kid with 4 brothers and sisters. So 5 children altogether. Just pretend. And the kids are little. Well, some are younger than others, of course. And some are, well, let's just pretend they're all from 9 years old to 14. Just pretend. Not that it really matters, but. Or just pretend there's 5 kids. Now, there's this opportunity to go to Disney World. Pretend. And the family, none of the kids have ever gone before to Disney World. And let's pretend that there is this trustworthy organization in which the parents would feel safe to allow their children to go to Disney World without them there chaperoning. Just all this is hypothetical. And there's a cost involved to go. And the parents sit down with their 5 children and they say, we're really sorry about this, but as you well know, this organization that we're all involved with has this opportunity for children to go to Disney World, but unfortunately things didn't work out the way we wanted to, and we don't have enough money to pay for all 5 of you. My made-up story is getting sad, huh? And so the parents say, well, we have enough money so that at least one of you, let's just say, I'm making this up, but let's say they don't know exactly the cost yet. But they do know at least an idea to know that at least one of the kids can go. At least one. At least one kid can go. So if you're hearing that and pretend you're one of the children, that would mean, what would that mean? At least one of you could go. Well, that means one person might get to go, one of the children, or maybe two children, or maybe three children, or maybe four children, or maybe all five children. We don't know yet for sure, but we do know at least one is going to get to go. We know that for sure. Now, once we find out, then we'll know exactly how many. So, what do you children think? We'll have to randomly pick once we find out. But right now we know at least one of you are going. If you guys are unhappy with that, knowing that you might get left out, then speak up now. My hypothetical story is getting serious, huh? And all of a sudden, a couple of the children say, we don't like this, Mom and Dad. It's either we all go, we don't think it's fair that not all of us will get to go. So we believe either, instead of at least one of us going, well, I'm trying to make this a statistical conversation. So let me say it this way instead. The children start to be a little frustrated about this, knowing that there's a chance that they may not get to go, even though we said at least one. And so the parents start to get a little frustrated as well, and then it kind of becomes a little bit of an argument, and emotions start to flare, and then the parents say, forget it. No one is going. No one's going. And why did I make all this story up? Because I want us to simply understand that the complement, the parents just used the complement to solve their problem. Because they wanted everyone to get to go. But they couldn't guarantee that, so they said at least one of you will get to go. We'll find out later. And because of the frustration and reluctance, the parents said, forget it. Well, then we're going to do the complement of what we just said, and the complement of at least one of you going is none of you are going. So I'm not trying to make some speech about children or families or Disney World, okay? I'm just trying to state that I wanted to plant something in our minds to understand this important idea and for it to appear as easily as it should be. And that is, if you hear the question, at least one. If it's at least one of the five children, well, that's either one person or two people or three people or four people or five people. And what's the complement of at least one of them? It's none of them. Go. What if there was 10 children? At least one of you children are going to get to go. What does that mean? One child could go, two could go, three could go, all the way up to all 10. What's the complement of at least one of those 10 children going? None of the children are going. So, if we know the probability of getting at least one is usually more difficult to compute. So, if we're asked what's the probability of at least one going, if we know the complement of, which is none of them are going to go, pretend the complement is none of them are going, and just pretend. The probability of that happening is 20%. Just pretend. The probability that no one is going is 20%. And the complement of no one is going is at least one of them's going. At least one of them's going. Well, those two are complementary events, so the two probabilities have to add up to 1, or to 100%. So if the probability of none of them is going, none of them are going is 20%, then the probability of the complement, which is at least one of them goes, would be 80%. Because the two are complementary events and they have to add up to 100%, or they have to add up to 1 in terms of proportional, numeric proportion values. Another way to write that down on a piece of paper is C. The probability of at least one, in this case there's not 5 children or 10, but just 2. At least one of the 2 would state event B. At least one of the 2 children are going to Disney World. Well, that's the complement of none of the 2 children are going to Disney World. And this one and this one have to add up to 1. Or another way to say that is the probability of at least one of them is equal to 1 minus the probability of none of them are going. If you know this one, none of them are going as 20%, is 0.20, 0.20, then 1 minus 0.20 would be 0.80. So, I hope that makes sense. So the probability that at least, let's go to the question. The probability, remember this was about picking 2 adults from this survey. The probability that at least one of the 2 adults picked randomly, stating that Franklin Roosevelt was the best president since World War II is, well, to compute the probability of at least one, what I hope we've accomplished here is that to compute the probability of at least 1, and it doesn't matter if it's at least one of the 2, or at least one of the 5, or at least one of the 10, it's always going to equal 1 minus the probability of none. So it's equal to 1 minus the probability that none of the 2 people would state event B. They would state FDR was the best president. They would not. And we know that's this right here, because we just did that in letter B. The probability they both would not state FDR was the best president. So it's 1 minus 0.677, which is 0.323. One minus 0.677. 0.323 to 3 decimal places. And there we go. .323. Are any of these probability values small enough to be considered unusual? Well, we talked about that already. And we said at letter A, which was the probability that both adults, the first adult selected, the second adult selected would state FDR was the best president, was 0.031. That is less than 0.05. So this would be considered an unusual event. This right here. So which of the events can be considered unusual? The event in part A is unusual because its probability is less than or equal to 0.05. So I hope that's okay, everyone. So don't forget that at least one is always going to be, can be found by using 1 minus the probability of none are going, or none, whatever the none is about. Number 10 is very similar to that problem. Instead of 2,069 in the sample survey, it's 1,200. Instead of talking about the president, FDR, they talk about, they think most celebrities are good role models. And now they ask you questions exactly like before. Okay. So that was number 11. Next, I'd like to help you with number 12. Okay, class, so now number 12. So it states here, the probability that a person in the United States has type B positive blood is 8%. Okay. So they didn't pick a sample of people. So there's not a sample of 2,000 people and they tested their blood. They're saying that out of all people in the United States, 8% have, about 8% have type B positive blood. Okay. Now, 5 unrelated people are selected at random. They need to stay unrelated so they don't all have a, if they're all the same family, maybe they have a higher chance or even lower chance of having B positive blood. I'm not sure how that works, but I learned it once a long time ago. Anyway, compute parts A through D. Find A. Letter A. Find the probability that all 5 randomly selected people will have this blood type B positive. Okay. So a person, randomly selected person in the United States having blood type B positive, that's the event that we're interested in. And I named it event B positive. So some authors like to keep the names of events. Oh, you have to use A and you have to use B and that's it. I don't necessarily agree with that. So I think we just should name it whatever we wish to make it more relevant and easier to remember that way. Okay, note. Because the population of interest is all persons, all people in the United States, and we do not have an exact count of all people in the United States, we cannot use the same numeric logic as in the FDR problem we just did, for example, where we knew there was 2,069 adults, and when you and 367 of them stated FDR was the best president, so then we could write 367 over 2,069, and then the second person would be one less, so 366 over 2,068. But we can't do that in this problem because we don't know. They didn't tell us, and nor do we know how many people are there exactly in the entire country. So even though selecting a second person with B positive blood is dependent on the first selection, it is an incredibly negligible dependency. Because we're talking about hundreds, close to whatever it is, 360, I lost track. I remember, I think I was in 5th grade or something. 3rd grade maybe, I don't know. I think the population was like 150 million, and now it's more than double. 360, 370, I don't know for sure. Google, I guess we could check it. So anyway, but we don't have that count. So numerically speaking, they are dependent in the sense like the FDR problem, where you would, once you take one person out, then there would be one less person, and then when you would have one less number in the denominator and the numerator, and then you'd multiply those two together. And then I showed you, you may remember I showed you with the calculator, I don't know if I still have it here, yeah, right here. And then I showed you, if we change this to 1702 over 2069, it was almost the exact same number. So the same idea with this. If we knew the number, pretend there's 380 million people in the United States, and we know that, and you'd have 380 million in the denominator, and pretend in the numerator we knew uh, 370 million had B positive blood. I know you're not going to remember those numbers, but the fact would be you'd have a huge number on the top and the bottom. Well, let me just do it with something without so many, not so big. Well, okay, whatever. So let's just say in the denominator we had 380 million people. So that's 3,800,000. One, two, three, 1, 2, 3. Okay, so there's 380 million. And pretend that's all the people in the United States, pretend. And the numerator, let's say we know that there are 38 million that have B positive blood. And so the probability you pick one person out of all the people in America, the probability that they would have B positive blood would be 38 million chances out of 380 million chances. Now times the second person. Now keep the first person out, and so now you only have in the denominator 379 million 999,999. And in the numerator you'd have one less, 37,999,999. And there you multiply those probabilities, and I don't know, you get that. Versus if we just now just throw that person back in, or just throw them back in, is it really going to make much difference in our answer? So if we were just to change this to the same 38 million, so instead of 0.009999, you get 0.01. So these are virtually the same number. 0.0999999 is really, really close to 0.01. If you round this even to 7 or 8 digits, you're going to get 0.01. So these are, numerically speaking, they're virtually equal to each other, which means even though in a formal sense, picking the chance that the second person having B positive blood is actually dependent on the first person in a numerical sense. But when these are out of so many people, then the probabilities are virtually the same answer, whether you treat these as dependent or treat them as independent. So that's what I mean by this. Even though selecting a second person with B positive blood type is dependent on the first selection, it is incredibly negligible. And this difference is so minimal, we can informally state that the two selections are numerically independent events. So you might be asked, if you're talking about a whole country, then you would say that these events are independent events, because the numerical part of it is so incredibly negligible. You can just say that they are independent. So since we do not have an exact count, we cannot do what I just did on Desmos. We can only compute using the given 8% value instead. This computed value will be virtually the same as the answer would be if we knew the exact count, which I just tried to show you. Thus, in problem 12, if we know, they're telling us that 8% of the population has B positive blood, and we don't know the count of all the people in the United States, then we're going to do it in this fashion right here. The probability of picking 5 people and all 5 having B positive blood type. So another way to write this is, remember I had written above, a person in the U.S. having blood type B positive, we're going to call that event B positive. So the probability that all 5 people selected having a B positive blood type is equal to P for probability, the first person being selected having B positive blood, and the second person having B positive blood, and the third person selected having B positive blood, the fourth and the fifth, all 5. This is the same as this, and can be computed, knowing that it would equal, because these can be considered independent events, then you can just write down each one of these individually and multiply their probabilities together. So it's equal to the probability the first person has B positive times the probability the second person has B positive, and so on. But what's the probability of any one person in this country having B positive blood? It's 0.08. 0.08. And so it's 0.08 multiplied 5 times, which is 0.08 to the 5th power, We can put that in our calculator. And so we have 0.08 raised to the fifth power, this button right here. And we get this, times 3.2768 times 10 to the negative 6 times 10, normally would make a number bigger, but it's 10 to the negative 6, which means you're making this number smaller by actually dividing by 10 6 times. Dividing by 10 6 times is equivalent to saying move this decimal place once to the left, a second time, a third, a fourth, a fifth, a sixth time. 6 times to the left. And so when we do that, it's the same as 0.50 is 1, 2, 3, 4, 5, and then 3, 2, 7, 6, 8. So this right here, 3.2768 times 10 to the negative 6. That's the probability value, but that's equivalent if you put the decimal point right there and divide it by 10 6 times. You move it once, twice, 3, 4, 5, 6 times. And you get this small number right here. And because it's so small, with so many zeros right here, that's why they ask us to round it to 6 decimal places. So 0.1, 2, 3, 4, 5, 6. So the 5 zeros and then the 3. The next digit after the 3 is a 2, so you leave this a 3. So it's 0.5 zeros and then a 3. 0.5 zeros and then a 3, which is incredibly small. Point 0, 1, 2, 3, 4, 5. 5 zeros, 3 to 8 or so. And then 0.5 zeros and a 3, and that's less, way less than 0.05. So this would be an unusual event. That's for sure. So impossible is this probability value, so incredibly small, that if we were to actually do this experiment and pick 5 people from the United States at random, and all 5 of them had B positive blood, that we should say, hey, that the chance of that happening is this right here. That is so incredibly small. We have 2 choices, 2 ways to believe, 2 different possibilities of how we should react. 1, a miracle just happened, and we, just by randomness, we got 5 people in a row that all have B positive blood. Or we could also think, because this should really not happen, the probability of it happening is so incredibly small, I choose not to believe that it's a statistical miracle, and instead believe that we really didn't pick these people randomly, or the testing of the blood type was done in error. Something of that effect. Anyway. Okay. Letter B. The probability that none of the 5 have type B positive blood. None of them. None of them. The probability that none of the 5 selected have a B positive blood type. note over here. The probability of a person being selected in the United States and not having a B positive blood type. Not. Well, that's the complement of having B positive blood type. This and this are complementary events. And so this probability and this probability have to add up to 1. Another way of saying that is the probability of this one, this right here, would equal 1 minus the probability of the complement of this. Or more specifically, the probability of a randomly selected person not having a B positive blood type. You randomly select a person and then you test their blood and they do not have, what's the probability that they do not have B positive blood type? It's 1 minus the probability that they would have B positive blood. So the probability of B positive prime, that means not having B positive blood type, equals 1 minus the probability of having B positive blood type, which is equal to 1 minus 0.08 from the directions up here. 1 minus 0.08 is 0.92. And so what does that tell us? The probability of randomly selecting a person in the United States and that person does not have B positive blood is 0.92, which is very high. Because not that many people actually have B positive blood, only 8%. So then there's 92%, the rest of us, or the other 92% of the country do not have a B positive blood type. They have one of the other 7. B negative, and all that. AB negative, AB positive, all those. So, what's the probability that none of the 5 selected people have a B positive blood type? None of them have it. So that is equal to the probability of the first person not having B positive blood, prime, that's the complement, and the second person not having B positive blood, and the third person not having B positive, and the fourth person not having B positive, and the fifth not having B positive. Because we talked about how these were independent events, then we can write the probability of all this is equal to the probability of each one by itself multiplied together. By the way, if the probability of an event the probability of a person, the first person having B positive affecting the second person having B positive is independent, well then also the complement of those events would be independent. The probability that the first person, or another way to say it is the second person not having B positive blood type is not influenced by the first person not having B positive. So anyway, you can now take each one of these probabilities, which is the 0.92 as we did over here, and you have 5, instead of 0.08 multiplied 5 times, you have 0.92 multiplied 5 times, which is approximately 0.659. And this is the exponent button, and then 5. And here we are. Oh, I typed something wrong here. 0.92. 0.659. Go one more digit, 0, so you keep that a 9. 3 decimal places, 0.659. And letter C, Now that we have the probability of none, remember that sad story with the family in the Walt Disney World? I hope that sticks in your mind. So now they're asking letter C. What's the probability of at least one of the 5 selected having a B positive blood type? What's the probability that at least one of the 5 would have B positive blood type? What does at least one of the 5 mean? One person could have B positive blood type. Two people could have it. 3 of them, 4 of them, or 5 of them. What's the probability of that? At least one of the 5? It's equal to 1 minus the probability of none of the 5 having B positive blood type. So once we find the probability that none of them have it, then we can find the probability at least one of them. And it's the 1 minus the probability that none of them, which is 1 minus the 0.659, which is the 0.341. And there's the 0.341. And then letter D, which of the events can be considered unusual? Well, remember we talked about this one, how unusual it was. So the event in part A is unusual because its probability is less than or equal to 0.05. It's way less than 0.05. This is way less. If you got by chance equal to 0.05, then that is also going to be considered unusual. If it's the probability value we compute, if we get equal to 0.05 or anything smaller, we can statistically say it's an unusual event. Okay? So that's number 12. We did 11, that was the FDR problem. We just did 12. 13. In a recent year, about 38% of all infants born in a country, so the infants, well, they're born, they're alive, and they were conceived through this in vitro fertilization procedure. Okay. I don't know if this is true anywhere, but that would be a lot, 38%. I'm sure this is made up. Of the in vitro fertilization deliveries, about 28% of them resulted in multiple births, twins, triplets, quadruplets, quintuplets, and so forth. So, event, infant born that was conceived through this in vitro fertilization process, we'll call that, I called it event IVF. A person can call it anything else. In vitro fertilization. Event. The infant born is one of a multiple birth delivery, meaning twins or triplets, and so forth. MB for multiple birth. Not, again, meaning 2 or 3 or 4 or 5 from that one conception. Letter A. Find the probability of on infant find the probability that a randomly selected infant was conceived through IVF, that's the first event, and was part of multiple birth, and the second event. Probability of the first event and the second event. The probability of the first event, the baby born, the infant born was conceived through in vitro fertilization, and the second event, the infant born was part of a multiple birth delivery. The probability of an event and a second event occurring, we know, hopefully we're comfortable now after this discussion, it's equal to the probability of the first event, which was the IVF, times the probability of the second event, which is the multiple birth, given knowing the first event occurred, the in vitro fertilization process. So what is this probability they're asking? Well, we need to know this one. The probability that an infant born was conceived through in vitro fertilization, and that is conceived through in vitro fertilization is 38% according to the statement, so 0.38 times the probability of the second event knowing the first event occurred. 28% resulted in multiple births of those that were conceived through in vitro fertilization. 28%. The probability of an infant being born having a multiple birth delivery, knowing that they were conceived through in vitro fertilization, is 28% chance. So this one is the 0.28, this one is the 0.38. Multiply these together and you get about 0.106. Since 0.106 is greater than 0.050, this is larger this time. This probability value is larger this time than 0.05, so this event cannot be labeled unusual. It's not. It's not a large probability, but it's not small enough to be labeled, quote, unusual. So times the 0.28, we said 0.106 to 3 digits past the decimal place, and there we go. Part B. The probability that a randomly selected infant that was conceived through in vitro fertilization process was not part of a multiple birth. Was not part. So it's a little bit, can be tricky when they're not nice and give us nice, comfortable words to decide what they're saying here. What I mean by that is, so letter B, find first the probability that knowing that the baby born, the infant born, was conceived through in vitro fertilization, knowing that, but the infant born did not have was not part of a multiple birth delivery. Was not. Prime. Complement. Not part of a multiple birth delivery. Randomly selected infant conceived through in vitro fertilization process was not part of a multiple birth. Was not. So this is equal to 1 minus the probability that, knowing that the infant born went through the in vitro fertilization process, knowing that, but then they were part of a multiple birth delivery. This right here and this right here are complementary events. Both say the baby born was conceived through the in vitro fertilization. The baby born was conceived through in vitro fertilization. This one says, knowing that the baby was conceived through IVF, they were not part of a multiple birth delivery. And this one is, knowing they were conceived through IVF, that they were part of a multiple birth delivery. So this and this are complementary events. If a baby was born and they were conceived through in vitro fertilization, then either they were part of a multiple birth delivery, meaning they had twins or triplets or so forth, or they did not. Baby was conceived through IVF. Baby was conceived through IVF. Either they were part of a multiple birth delivery, or they were not. So we need to realize that they are complementary events, and therefore, if we need to find one of them, and if we know the other one, the complement, which we do now, we know this right here, they gave it to us, the 0.28, this one. That's right here. So it's 1 minus the 0.28, which is 0.720. Compare that with, this is where it can get a little harsh, frustrating. The probability, compare this statement with this statement. This is saying the probability this means of all babies born, what's the probability that they were conceived through IVF, in vitro fertilization, and they were not part of a multiple birth? This can be easily confused with this. This one means they both sound almost the same. Event IVF, event not multiple birth delivery. Not multiple birth delivery, event conceived through IVF. They sound almost the same. The difference is, this one right here is out of all babies born. Out of all babies born, any type of baby born. Meaning not they were conceived naturally or any other way to be conceived other than in vitro fertilization process. To compute this probability, which they did not ask, but we would do the following. The probability of the baby, infant baby, being conceived through in vitro and they were not part of a multiple birth, you would need to know the probability that they went through in vitro, which we do, 0.38, times the probability that they were not part of a multiple birth, knowing that they were conceived through this in vitro process, which is this probability right up here. And then you multiply 0.38 and 0.720. and you get 0.274. So even though this and this sound almost the same, this probability is so much smaller, 27.274, 27.4%, and this one is 72%. 27.4%, 72%. Big difference. Because this is out of all babies born, period. There's a 27.4% chance that they were conceived through in vitro and they were not part of a multiple birth. The chance that a randomly selected infant baby being conceived through in vitro and not being part of a multiple birth is 27.4% chance, if you believe all these numbers. I'm not saying believe the computations, but believe the original numbers they gave us. What's the problem? What's this one? Knowing that, so now you're talking about a subgroup of babies born. This condition. So knowing that just from the babies conceived through in vitro, the probability of those not being part of a multiple birth, is 0.720, 72%. Okay. .720. Would it be unusual for a randomly selected IVF cycle to result in a pregnancy and produce a multiple birth? And produce a multiple birth. Well, they made it sound difficult, but that's what this one is. They went through IVF, the baby was conceived through IVF, and they were part of a multiple birth. That's what this is. They just tried to make it sound confusing here. So that's 0.106, and we stated that that was larger than 0.05, so it's not unusual. No, this is not unusual because the probability is not less than or equal to 0.05. $14 is very similar to 13. So I did one of those, now you do the other one. This one is also for you. 15, 16, and 17 are almost exactly the same. So I want to help you with one of those two. And here we go. So they give us some events. One of the events is the airplane departs the airport on time. I just made up a name, event ADT. Airplane departs on time. They happen to give us this probability. Now, of course, I don't know, these are probably made up or something, but who knows? The probability that an airplane, a randomly selected airplane that departs the airport, the probability that they depart on time is equal to 0.91. 91% chance. Or 91% of the time they depart on time. The airplane arrives on time. The airplane goes through their flight, and they land, and they arrive on time. AAT, airplane arrives on time. They give us that probability as well. The probability randomly selected airplane arrives on time is 0.87. So, the probability that an airplane flight departs on time is 0.91. The probability that a flight arrives on time is 0.87. The probability that a flight departs on time and arrives on time is 0.84. They depart the airport on time and they arrive on the airport on time. When they land, of course. Okay. The probability that the airplane departs on time and the airplane arrives on time is 0.84. Question. The probability that a flight arrives on time, it lands and arrives at the airport on time, given, oh, there's a restriction, conditional, given that it departed on time. Sounds almost the same as this one. It arrives on time, given that it departs on time. Well, of course, this has to be the first event. The plane leaves the airport, goes on its flight, it departs on time, leaves, takes its flight, lands, and arrives on time. And that's what this is too, but this is and this is given. Given that the first event we know occurred, given that we know the airplane departed on time, what's the probability that it arrived on time? Find the probability that, given that the event airplane departed on time, given we know that that occurred, what's the probability that it arrived on time? So they just twisted the question. They normally ask us to find this one. And normally we use this general formula. The probability of a first event and a second event was equal to the probability of the first event multiplied by the probability of the second event given the first event occurred. This is what we've been using throughout the lesson. Well, now, and normally they give us this one, and they give us this one, and we multiply them together, and we answer the question, which was this. And now, that's what we did throughout most of the lesson. So, we were asked to find this probability statement's value, and they gave us these two probability statement values. So they had to give us two of the three. Well, all they're doing this time, class, is giving us a different two of these three. Instead of giving us these two, and then we have to find this one. Instead, they give us this one again, but they don't give us this one. They do not. But then instead, they give us this one. And this one is the same right here. With our question, instead of writing it like this, generally, the probability of event airplane departs on time and the event airplane arrives on time, we know, according to this general formula, equals the probability that the airplane departs on time, the first event, times the probability of the second event, airplane arrives on time, given that it departed on time. But this time, they are not giving us these two probability values. They're giving us this one, yes, just like always, but they're giving us this one. And they're not giving us this one. That's all. So they give us two of the three here. 1, 2, 3. Normally they give us these two. And then we multiply them and we get this. This time they are giving us this one still, but not this one. And then they're also giving us this one. And what is this one? The 0.84. What's this one? Our airplane departs on time, 0.91. And then they're not giving us this one. So we have 1, 2 out of the 3 probability values. And now we have a little equation to solve. So then, instead of normally we would multiply these two and we would be done, but now we have to do it slightly differently. We need to solve for this one. So to solve for this probability statement, we need to get rid of this multiplication of 0.91. We need to get rid of this multiplication of 0.91. And the inverse mathematical operation to multiplication of 0.91 is division of 0.91. The inverse of multiplication of 0.91 is to divide by 0.91. So we divide both sides by 0.91. When you divide it on this side, 0.91 divided by 0.91 is just 1. 1 times this still. You don't need to write the 1 times in front if you don't want to. And then we just divide 0.84 divided by 0.91, and whatever that turns out to be, which hopefully is this, is the value of what we're looking for. So 0.84 divided by 0.91. .923. The next digit's a 0, so we keep it at 923. 0.923. And that's it. There's only one part this time. Now they wrote this a little differently. You could do it. It's the same thing I did. I kept it the way you're used to instead. I just kept it this way. What they did is they wrote solve for this, and instead of dividing by 0.91 all the time, they just divided by this. And they wrote this is equal to this one divided by this one. But you can do it that way or just keep it the way I wrote it, and it's the same thing. Okay. So you're going to do number 16 is the same question. They're almost the same numbers. So that's for you. And these last 5 questions are just conceptual questions if we understanding the topics and the terminology that we have used in this lesson. So this one is the difference between independent and dependent events. I'm going to let you look at that. Same idea here. What does this notation mean? Explain how the complement can be used to find the probability of getting at least one item of a particular type. The probability of getting at least one of a particular type. At least one of the 5 children are going to go to Disney World. How can we use the complement to compute that type of probability statement of probability of at least one? The complement of at least one is none. The complement of at least one is none. The complement of at least one is all. That's wrong. All. So A and B are wrong. So it's C or D. The complement of at least one is none. So the probability of getting at least one is equal to 1 minus the probability of none. The probability of getting at least one item is equal to the probability of none minus 1. So they switch these around. Which one is the right one? I hope you remember it's this one. So C. The probability of at least one of us going to Disney World is equal to 1 minus the probability that no one goes. And 22 is asking you about this, true or false. I'll let you all try that one. Okay, class, so it's a long discussion. I get a little tired as well, but I hope this helps you. Normally I split this up into 2 videos, but I lost track of time, so I'm probably going to have to upload this video to YouTube. So when you view it, when you open it up in your Blackboard course, it'll show up on YouTube versus what you're used to, because once we get over 2 hours, the other system that I've been using doesn't allow you to have the video over 2 hours. So that's why. Okay, so I hope you all are doing well. I hope this can help you. Be patient. And we'll see you next time for section 3.3 class. Okay, so this is Mr. King, of course, and saying good night and goodbye. Thank you, class.